What shape do you get when you take an ordinary piece of string and hang it between your fingers, like so? Let's draw a rough approximation of the string and clear off the blackboard. We'll need to make some idealized assumptions about the string. First, that it's perfectly flexible, and second, that it has uniform density throughout. Given these assumptions, I would have assumed that the correct shape would be a parabola, but this is not correct. A parabola is a little bit skinnier than the actual shape of a hanging string, and it's not due to some defect in the real-world string that I used. Even in theory, it's not a parabola, as we'll see. In order to figure out the shape of the string, we're going to need some inputs from physics. Specifically, we're going to need to start by talking about gravity and center of mass. It is a consequence of Newton's laws of physics that the gravitational force between two bodies acts on their centers of mass. This remains true even if the body is non-uniformly shaped, such as a cat. We can conclude, therefore, that the hanging string will hang in such a way that its center of mass is as low as possible. This is the physical principle that we're going to use to calculate its shape. Let's review how to actually calculate the center of mass in practice. Suppose we have 5 different objects, each with different sizes and therefore different masses, and we want to calculate the x and y coordinates of the center of mass of the system as a whole. The x coordinate is the weighted average of the x coordinates of each individual object, where the weighting factors are given by the masses of the objects. Similarly, the y-coordinate is given by the weighted average of the y-coordinates of the centers of mass of the individual objects. That tells us how to calculate the center of mass of a finite collection of simple objects like little balls. But it doesn't tell us how to calculate the center of mass of a smooth curve. In order to do that, we're going to approximate the smooth curve by a collection of line segments, and we're going to calculate the center of mass of all of those line segments taken together as one single system. We'll use that as an approximation for the center of mass of the curve. By taking a limit as the number of line segments approaches infinity, we'll get an exact answer for the center of mass of the curve. In order to make this approximation trick work, we're going to need to calculate the masses of all of the individual line segments. Now, since we assumed that the string was uniform throughout, that means that the masses of the line segments is just going to be proportional to their length. Assuming the curve is the graph of a smooth function y of x, we can use a little bit of calculus together with the Pythagorean theorem to write down a formula for the lengths of the line segments in terms of their widths. Using this formula, we can calculate the center of mass of the system consisting of all of the line segments used to approximate our curve. Taking a limit of this formula as the number of line segments approaches infinity and their widths approach 0, we get a nice integral formula for the y-coordinate of the center of mass of the curve. Putting it all together, we need to find the function y of x, which minimizes the y-coordinate of the center of mass, given by the integral from a to b of y times the square root of 1 plus y prime squared with respect to x. Here a and b are just arbitrary endpoints, don't really matter. Now we're going to do something slightly scary. Consider this integral as a function, let's call it L, of y. But remember, y is itself a function of x. So we're considering a function which takes functions of x as inputs. That's not normal. Normally in calculus, we consider functions of real numbers or maybe functions of vectors. We don't consider functions that take functions as inputs. So how can we deal with that? Part 2, Infinite Dimensional Calculus. Actually, it's called Calculus of Variations, but that's kind of boring. All right, before things go too far off the rails, let's do a brief review of one variable calculus. We're given a function y equals f of x, and we want to find the maximum and minimum values that it takes. Step 1 is to find the critical points of the function. That is the place where its derivative is 0 and its tangent line is flat. The maximum and minimum values have to occur at one of these points, or potentially the endpoints. So all we do is we list out all the critical points and all the endpoints and just check through until we find the maximum and minimum value. Multivariable calculus works in more or less the same way. Now we have to probe a point from multiple different directions in order to ensure that it's a critical point. For example, a function of 2 variables has a tangent plane attached to it instead of just a tangent line. Sure enough, if the function attains its maximum or minimum value at a point P, then the tangent plane at that point has to be flat, or in other words, the derivative of the function is zero in an appropriate sense. In particular, the derivative of the function vanishes along any direction emanating from P. This property characterizes the concept of a critical point in finite dimensions, and we're going to use it to generalize to the setting of infinite dimensions. To be more precise, in order to find the directional derivatives of a function z of x, y, start at a base point P and move a very tiny amount epsilon in the direction of a vector v. Call the point P plus epsilon v a perturbation of P. We then take an ordinary one-variable derivative of the function z with respect to this perturbation. If these derivatives are zero, no matter what direction we perturb in, then the point P had to be a critical point. Now we're ready to do calculus in infinite dimensions, also known as the calculus of variations. The setup is we have a function L which takes as input another function y. Now the function L we're going to look at has a very specific form. It's going to be a definite integral from endpoints a to b of some function f which depends on y, the derivative of y, and possibly the variable x, y being a function of x. We can compute the directional derivatives of L almost exactly the same way we did in the multivariable case. We start with an initial base point y, we move a tiny amount epsilon in the direction of some other function h, which we call a variation. Now it's convenient to assume that the variation doesn't do anything at the endpoint, so h of a equals h of b equals 0. The formula for the directional derivative of the function L defined in this manner is almost exactly the same as it was in the finite dimensional case. Looks a little bit more unwieldy because there's integrals and because we're perturbing in the direction of a function instead of the direction of a vector, but the intuition is very much the same. We just can't really draw a picture of the tangent plane anymore since the tangent plane is now an infinite dimensional space. Nevertheless, it is kind of possible to visualize the variation process. So we start with a nice smooth function y, this is our base point, and we introduce a variation function h, which just kind of squiggles around. It could really do anything. I just made one that kind of squiggles up and down a little bit. Then we add the two together, and that's our perturbation point. So we add y plus epsilon times h, and we get another curve, the pink curve, which kind of squiggles around y. Now we want to calculate these directional derivatives a little bit more explicitly. Sort of like in the one variable or multivariable case, the goal is to end up with an algebraic equation that we can solve in order to find critical points. We want to kind of do the same thing here, only instead of an algebraic equation, we're going to get a differential equation. Now, the manipulations that we're going to do in order to get to that differential equation are a little bit tricky, but don't worry about them too much. As long as you understand the idea of computing directional derivatives in terms of perturbations, that's the important thing. So let's explicitly write down our perturbation. It's y epsilon equals y plus epsilon h. And then let's do a couple of manipulations. So we'll plug things into the definition of directional derivative, and we'll differentiate under the integral sign, and we'll use the chain rule for partial derivatives. Now if we take the second term inside the integral in our formula for the directional derivative and apply integration by parts, then things simplify quite dramatically. The formula for the directional derivative becomes the integral of h times some expression involving the partial derivatives of f and the derivatives of those partial derivatives with respect to x. Now recall that the concept of a critical point is characterized by the property that the directional derivative is zero along every direction starting at that point. Now in this context, the role of a direction is being played by the function h, and so what we conclude is that the integral from a to b of h times that expression involving the partial derivatives of f has to be zero for every possible function h. The only way that that can happen is if the expression inside the parentheses is itself zero. That's a fact from real analysis. So this gives us a differential equation involving y, y prime, and x. The solution to this differential equation are precisely the critical points of L. And of course, if L attains its maximum value at some function y, then y has to be a critical point. So by solving this equation, we can hope to find the optima of L. So this equation has a name. It's called the Euler-Lagrange equation. And we're going to use a variant of the Euler-Lagrange equation to solve our problem involving hanging strings. The specific form of the Euler-Lagrange equations that we're going to use applies in the case where the function f doesn't depend explicitly on x. Like when you write down a formula for it, you only see y and y prime terms. In that case, it turns out that the Euler-Lagrange equations are equivalent to the statement that f minus y prime times the partial derivative of f with respect to y prime is a constant. And this will turn out to be easier to work with in a lot of different cases, such as the hanging rope case. I'm not going to go through the complicated manipulations that show that the Euler-Lagrange equations are equivalent to this equation in the case where f doesn't explicitly depend on x, but perhaps that will appear in a forthcoming blog post. Part 3, the shape of hanging string. We're almost there. Our work is almost paid off. Let's now apply what we've learned about infinite dimensional calculus to our hanging string problem. So as you recall, the hanging string problem is equivalent to minimizing the function L of y equals the integral from a to b of y times the square root of 1 plus y prime squared, all with respect to x. So this is in the form of the calculus of variations problem that we posed in the last section, where the function f of y, y prime, and x is given by the y times the square root of 1 plus y prime squared term. You'll note that this doesn't explicitly depend on x, so we can just solve the alternative formulation of the Euler-Lagrange equations that we presented in the last slide. Now, if you remember your rules for calculating derivatives from Calc 1 or Calc 2 or whenever one learns that stuff, you might be able to calculate the partial derivative of f with respect to y prime. And plugging that back into the Euler-Lagrange equation results in a nice, if a bit complicated, differential equation involving y and y prime. The solution to this equation is going to be the exact curves that we're looking for that describe the shape of a hanging string. Now luckily, we can rearrange this rather complicated differential equation into a slightly simpler looking differential equation that we can actually solve explicitly. So integrating both sides with respect to x and rearranging things a bit, we get, drum roll please, y equals hyperbolic cosine of x up to some constants. And there it is. That is the correct shape of a hanging string. When you plot the graph of hyperbolic cosine, you get something that looks a little bit more realistic from our experiment at the beginning of this video, something that hangs a little bit more flat than the parabola does. And so sure enough, this looks plausible as the shape of a hanging string. So that's it for this video. I hope you found it interesting and useful, and thank you for tuning in. Calculus of variations is a really interesting and powerful tool. It's all over the place in modern mathematical physics, so it's worth looking into more if you found this video interesting. So once again, thank you for tuning in, and thank you also to 3 Blue 1 Brown for putting on this competition again. Gets us all off our butts and communicating about mathematics. Take care.